Hello and welcome to this new video. In this video, we are going to solve exercises 7 through 10. But before I start solving exercise 7, I need to add something that I didn't state explicitly in the course, in the lectures, but this is something that you can easily deduce from the ideas in the lecture. Okay. So let us revisit the notion of limit point or accumulation point. So if we have a subset A of R, a point X in R is called a limit point or accumulation point of A is if every neighborhood of X meets A at a point different from X. Okay, or otherwise stated, it meets A without X. Okay, but since any neighborhood of X contains an interval of the form X minus epsilon and X plus epsilon, and X minus epsilon, X plus epsilon is also a neighborhood of X, then it's equivalent to saying, so X is a limit point of A, means that any interval of the form X minus epsilon, X plus epsilon meets A without X. Okay. And it's useful to denote the set of limit points of A by A prime. Okay. But don't confuse A prime with A bar. A bar is larger because A bar, the set of adherent points, can be split into two sets: the isolated points of A and the limit points of A. Okay? So the first thing that you can deduce from the ideas in the lecture is the following fact. So there is an equivalent between saying that X is a limit point of A and the condition that there exists a sequence Xn of A that converges to X, but Xn is never equal to X. Okay? So this is something parallel to proposition 1.6, which gives a characterization of the fact that X belongs to A bar. So note the difference. In proposition 1.6, we said that X belongs to A bar is equivalent to there exists a sequence Xn in A that converges to X, but we didn't require that Xn is different from X. Okay? Now the proof is not difficult, so let us prove 1 implies 2 first. In the condition of limit of the definition, take epsilon equal 1 over n for n equal 1, 2, 3, etc. Then, by definition, there exists the intersection x minus 1 over n, x plus 1 over n with A without x is not empty. So it contains a point. Of course, this point depends on n. Okay? So what do we have? Xn minus x, an absolute value, is less than 1 over n. Okay, so Xn by construction converges to X, and also by construction Xn is never equal to X. Okay, so 1 implies 2. 2 implies 1. Okay, let U be a neighborhood of X. We can take U of this form, X minus epsilon, X plus epsilon. Since Xn converges to X, then by our definition of convergence, all the elements Xn will be in U starting from a certain rank, n0. So in particular, Xn0 belongs to U, and of course, since Xn is a sequence in A, Xn0 is in A. Okay? But by assumption, Xn is different from X, so actually Xn0 belongs to this intersection. Okay? So, but this is true for every neighborhood. Okay? So X is a limit point of A. So the proof is completely parallel to proposition 1.6 that you proved in the lectures. Okay? So this is very useful actually to detect limit points, as we shall see now. Now, the second fact is something that I stated in the lectures, but I didn't prove. In fact, the intersection, if X is a limit point of A, this intersection is not only not empty, it's actually infinite. Okay? And therefore, U intersected with A is infinite because these two sets differ by a point X. If this is infinite, and vice versa. Okay? So let us prove that this intersection is infinite. So we reason by contradiction. If it's not infinite, then it's equal to some finite set. I know it's not empty, so it at least contains one element. Okay, suppose it contains k elements. K could be 1. Okay, now remove A1, AK from U. Then we get an empty intersection, right? There's no element in this intersection now. Okay, but now observe the following. We know that singletons or one-point sets are closed in R. So it follows that finite sets are also closed in R. So the set A1, AK is closed. When I remove, okay, I can always assume that U is open actually, because if a neighborhood is not open, I can take a smaller open neighborhood. Okay, so we can always assume that our neighborhoods are open. Now, when we remove a closed set from an open set, the resulting set is actually what? Is actually open. Okay, because it's the intersection of two open sets actually. Okay, but X is here actually because X is different from A1, AK. So this is an open set containing X. Okay, but since X is in A prime, in particular it's in A bar, actually, or yeah, since X is in A prime, this neighborhood should meet A without X, but it doesn't. And this is a contradiction. Okay, so we prove that the intersection is not only not empty, it's actually infinite. Okay, now let us move to exercise 7. We consider the set of elements of the form 1 over n plus 1 over m, where n and m are positive integers. Okay, we can list, it's a countable set actually, we can list the elements. The first question is to find the limit points of A, and the second question is to answer whether A is closed or open or compact. Okay, let us start with the first question. Now, A is actually a countable set, so it's itself a sequence, right? Now, if we fix m, so we have two variables here, m and n. Fix one of them, fix m, and consider the sequence xn given by 1 over n plus 1 over n. Okay? Now, when m is fixed and n tends to infinity, xn tends to what? 1 over m. But xn is never equal to its limit. Therefore, according to the first fact, 1 over n is the limit point of A, right? But m was arbitrary. So the whole set, 1, 1/2, 1/3, etc., is included in the limit, are limit points of A. Okay, it's included in A prime. Okay? And now, if we take n equal m, we get the sequence 2 over n. So 2 over n is a sequence of A. It's a particular sequence of A. And it converges to 0, but it's never equal to 0. Therefore, according to fact 1 again, 0 is also a limit point of A. Therefore, we have proved something, that the set that we counted already in exercise 5, the set 1, 1/2, 1/3, etc., together with 0, is contained in the set of limit points. Now, whenever we have an inclusion, we ask ourselves, is the reverse inclusion, do we have equality? And the answer here is yes. So we have to prove the reverse inclusion, and in this case, we would have determined A prime, the set of limit points of A. Okay, so we can reason by contraposition if you like. So if we want to prove that A prime is contained in this set that I call B for simplicity, I have B contained in A prime. I want to prove that A prime is contained in B. So it's enough to prove that if X is not in B, then X is not in A prime. So X is not a limit point. Okay, but it's a contraposition. So suppose that X is in the complement of B. Now we proved in exercise 5 that B is closed, right? And B was actually the closure of this set, 1, 1/2, 1/3. Okay? So we have what? We have a point in an open set. So by definition, we can find a neighborhood of X totally contained in the complement. This is by definition of an open set. Okay, so otherwise stated, this neighborhood of X doesn't meet B. Okay. Okay. So what does it mean? It means that, in particular, a point in B cannot be here, cannot be in this neighborhood. Okay? So a point in B, in particular, take 1 over m. So 1 over m is not here. This is not in this interval. So it means that its distance to X is bigger or equal than epsilon, because it's outside the interval. So the distance between the center of the interval is bigger or equal than epsilon, right? And this is true for every m. Okay. Now I claim that the interval x minus epsilon over 2, x plus epsilon over 2, intersects A only at finitely many points. And it will follow actually from fact 1 that x is not a limit point of A because the intersection would be infinite. Okay. So consider a point in this intersection. Actually, I know that the intersection is actually I know nothing about x. I don't know that if x belongs to a bar or not. Okay, so but suppose that if it's empty, then fine, then you have proved. So suppose that it's not empty, and pick a point in the intersection. Now, since this point in the intersection that I call small a is in capital A, then it's necessary of the form 1 over m plus 1 over m for some integers n and m, right? By definition of A. Okay, so since this element A is an x, then its difference with x is between minus epsilon over 2 and epsilon over 2, because it's this 1 over n plus 1 over m is in this interval, right? Okay. Fine. Now, we already observed that since x is not in B, then its distance to 1 over m is at least epsilon. Okay, so we have two cases because we don't know the sign of this. If this is positive, then we get 1 over m minus x equal to its absolute value is bigger. If it's negative, then we have x minus 1 over m, it's bigger than epsilon. So taking the opposite, we get 1 over m minus x is less or equal than minus epsilon, okay, depending on the sign. Now, I claim that the first case cannot happen. Why? Because I wrote in this way actually okay, why? Because now consider this inequality in equation 1. And consider the second inequality. Okay, and now add them together. Minus epsilon over 2 plus epsilon is epsilon over 2. X minus 1 over m minus 1 over m plus 1 over m minus x. So the x and 1 over m cancel. I get minus 1 over m. So I get a positive number less than a negative number. So this case cannot happen. Therefore, we are in this case. And now we add this inequality to the second inequality of 1, to this one. Epsilon over 2 minus epsilon is minus epsilon over 2. And once again, you have cancellation here, so you get minus 1 over n. So you get minus 1 over n is less than minus epsilon over 2. So 1 over n is bigger than epsilon over 2. Taking the inverse, we get n less than 2 over epsilon. Okay? Since n and m play the same role, we also get m is less than 2 over epsilon. Okay? Now, there are finitely many integers between 0 and 2 over epsilon, no matter how epsilon is large. Okay? So it means that there are finitely many elements, since there are finitely many couples in M. If A is equal 1 over n plus 1 over m, then there are only finite, the intersection is finite. Okay? So there's an upper bound on n and m. So the intersection cannot be infinite. And this proves the claim. Now, as you observe, it follows from fact 2 that X is not an A prime. Okay? And that's it, actually. So this proves the reverse inclusion. Okay, we prove that if X is not here, then it's not here. So we have equality. So we have A prime contained in B, and therefore we have equality. Okay, so we determined completely the set of limit points of our set under consideration. Okay, I agree that it's not trivial. It's a little bit difficult, takes some work, but you will get used to this kind of things. Now, second question, we want to say if A is closed or compact or open. Okay, since 0 is a limit point of A and 0 is not in A, therefore A is not closed. This is by proposition 1.6. So we have 0 is in A bar but not in A. Okay, so A is not closed, and therefore it's not compact, right? The question of yeah. So if it's not closed, it's not compact, right? And since A is contained in the rational numbers, there can be no non-trivial interval inside A. So the interior of A is empty, right? So A is not open, actually. You can see it in two ways. So we already observed such this idea before. We encountered this idea that often set with empty interior before. Okay? So since A is different from a circle, A is not be empty. Or you can just say, since there's no non-trivial interval in A, then A is not open. Right? Same thing, actually. Okay, so this concludes exercise 7. Now, there are also two facts that I didn't mention explicitly in the lecture, but or you can deduce. A set is open, a subset of A of R is open if and only if it's equal to its interior, and it's closed if and only if it's equal to its closure. Okay, this is something that you can deduce from the definitions. Try to write the proof. It takes 2 lines. Of course, if A equal a circle is open by definition, so A is open. If A is open, then A is the biggest open set in A, so it's equal to a circle, right? And same thing for the second one. So just an easy consequence. Exercise 8 is close to exercise 7, but here we also have actually so we have a set consisting of 2 sequences actually. Now I will write the details. So we have to determine the interior, the closure, and the limit points of A, and to say if A is closed, open, or compact. Okay. Since A is contained in the rational numbers, then its interior is empty. So, of course, A is not open. So this answers question B. So same thing as before. And now let us look at A more closely. When we take n equal 1, we get minus 1 over 1 plus 1 over 1, so minus 1/2. When n equal 2, we get 1 here, minus 1 to the 2, over 1 plus 1/2, so it's 1 plus 1 over 3/2, so it's 2 over 3. And then we get minus 3 over 4, then 4 over 5, and so on. So A actually consists of 2 sequences. One converges to minus 1, and it's decreasing actually. It decreases because it starts from minus 1/2, then minus 3 over 4, then minus 5 over 6. So it decreases to minus 1. And the other one, 2/3, 4 over 5, 6 over 7, increases to 1. And this structure will help us to find the closure and the limit points. Okay? And the 2 sequences are far apart from each other. They don't mix. Okay? One is in the neighborhood of minus 1, and the other is in the neighborhood of 1. So you can draw a picture if you like. Okay? Yeah, this is what I said. So we found a sequence in A converging to -1. Therefore, 1 is an A bar. So -1 is an A bar. And we have the second sequence is converges to 1, so 1 is an A bar. Right? And actually, since these sequences are different from 1 and -1, by fact 1 in the beginning of the video, actually -1 and 1 are limit points. So not only they are in A bar, but they are limit points of A. Okay, so we have proved that in particular. Now I want to determine A prime and A bar both. So let us first concentrate on determining A bar. Okay, so we have proved that A, of course, A is contained in A bar by our definition, and I proved that -1 and 1 are both points in A bar because they are limited. So note that A prime is contained in A bar in particular. Okay, so I have this inclusion, and I would like to prove the reverse inclusion. Okay, now there may be several ways to prove the reverse inclusion. One way, we reason as in exercise 5, right? So in exercise 5, we had just one sequence, one strictly decreasing sequence, and we proved that its A bar is A union its limit. Here we have just two copies of the same thing. So we have a sequence converging to -1 and the sequence converging to 1. So we can, so we can prove that A union -1, 1 is closed, and since A bar is the smallest closed set containing A, then we have A bar contained in A union -1, 1. Okay, so very similar to exercise 5, but instead of one sequence, we have two sequences. Okay. But the proof that A union -1, 1 is closed is not totally trivial, so you have to rewrite it. If you don't believe me, just rewrite it. Just copy, try to adapt the proof of exercise 5 to this situation. Okay? Now, the second way, we know that A is the union of two disjoint sets, A1 and A2. So the closure of A is the closure of the union. But we can prove that the closure of the union is the union of the closures. This is something not very difficult to prove. And now, as exactly as in exercise 5, A1 bar is just A1 union -1, the limit. And A2 bar, the closure of A2, is A2 union its limit. It's not true for all sets, but in this particular context, it's true. Therefore, A bar is A union -1, 1. Okay, so this concludes. Now we have to just specify the limit points. We already observed that 1 and -1 are the limit points of A, but we want to prove that they are the only ones. Okay. So otherwise stated, we will have to prove that the points of A1 are isolated and the points of A2 are isolated in A, both. Okay. So if you take the first sequence converging to 1 and which is increasing, okay, so this is a sequence that it's actually strictly increasing. So between two consecutive terms of the sequence, there's no third one. Okay, so between xp -1 and xp +1, xp is the only point that belongs to A. Okay, so try to we did something similar actually in the lectures. So it means that the element x to p is isolated in A. Okay, and similarly for the other sequence, but the other sequence is actually decreasing, right? So we can prove the same thing. So this proves what? This proves actually that all points of A are isolated. Okay, and that's it. Okay, so point of A bar, we know that A bar is A union -1, 1, 1 and 1. The points of A are isolated, and minus 1, 1 are the limit points. So this completes the picture. Okay, so therefore, now it's clear. Now B is very easy now. A is not open because it's contained in the rational numbers. And since A is different from A bar, A is not closed, and therefore not compact. But it's bounded. So bounded but not closed, so it's not compact. Okay? Or we can just say 1 is in A bar but not in A. So A is not closed. Just the same idea. Okay. Exercise 9 is very similar to exercise 7, actually. It's just a copy, but instead of 1 over m, 1 over n, I have two sequences, two decreasing sequences, 1 over 2p and 1 over 7q, right? But the picture is exactly the same, but it's not symmetric, okay? So, okay, once again, this is B consists of rational numbers, right? Because they are fractions. So the interior of B is empty because the interior of Q is empty. So B is not open, right? And if you reason as an exercise, you just have to write things down. I will not repeat it. But instead of the set 1 over n union 0, I have two sets here. 2 to the power minus p, 1 over 2p, if you like, and 1 over 7q, okay? And they are not the same here. So B bar is B union these two sets union 0, because the two sequences converge to 0. And the B prime is just what we add to B to obtain B bar, actually. So actually, once again, the points of B are isolated, and all these points are limit points. Okay? So I suggest that you write on your own the proof by adapting the proof of exercise 7 to this new case. So same thing, actually. And of course, B is not open, it's not closed because it's not equal to a B bar, and therefore it's not compact. So this is an easy question. Okay. Last exercise for in this video. I want to show that the rational numbers inside 0, 1, between 0 and 1, is not compact. Okay. And we have several ways of proving that. First way, I can show that A is not closed. So the intersection of the rational numbers with 0, 1 is not closed. If it's not closed, then it's not compact. Okay, why it's not closed? Let us see what is the closure. Of course, our intuition tells us that it must be 0, 1 because any number in 0, 1 could be approximated by a sequence of Q of rational numbers inside 0, 1. Okay, if you understand this, then fine. But if you want a rigorous proof, here's the proof. To prove that the closure is inside 0, 1. Okay, so double inclusion, right? Since 0, 1 contains A and 0, 1 is closed, then it contains a bar because A bar is the smallest closed set containing it. Now, the reversed inclusion will distinguish between three cases. X is inside, is in the interior of 0, 1. So I suggest that you draw a picture. Okay, so 0, 1 is open and X is in 0, 1. So we can find a number epsilon 0, a positive number epsilon 0, such that the interval of center X and radius epsilon 0 is contained in 0, 1. And by the way, we have a formula for epsilon 0, if you like. We can take the biggest epsilon 0. We did that in the lecture, but it's not important here. Okay, now if you take epsilon less than this constant epsilon 0, what do we get? The interval of center X and radius epsilon is contained in the interval of center X and radius epsilon 0, right? Because epsilon is less or equal than epsilon 0. And this second interval is contained in 0, 1, right? Now, choose so this is in the open interval x minus epsilon, x plus epsilon. Choose a rational number because I know that any non-trivial interval contains rational numbers. So this rational number will be in Q and in 0, 1. So it will be where actually? It will be in A and in x minus epsilon, x plus epsilon. So therefore, this intersection is not empty. Okay? And therefore, but this is true for every epsilon less or equal than epsilon 0. Now, you may say, well, we can already deduce actually that x is an A bar because it's enough to prove this for epsilon small enough. Why? Because what happens if epsilon is bigger than epsilon 0? It's easier. Because if epsilon is bigger than epsilon 0, then x minus epsilon, x plus epsilon is bigger than x minus epsilon 0. Okay, so when the radius becomes bigger, the interval becomes bigger. Okay? And since we proved that this intersection is not empty, then the bigger intersection is also not empty. Okay? So, therefore, we proved that for every epsilon, x minus epsilon, x plus epsilon meets A. By proposition 1.6, x belongs to A bar. Right? We are not obliged to treat this case because it's enough to just prove it for epsilon small enough. If it's true for epsilon small enough, then it's true for all epsilon. Right? Now, second case, x equals 0. Take here in this case, for instance, epsilon 0 equal 1/2. Right? Same thing. So the interval 0 epsilon is contained in the interval 0 1/2, which is contained in 0 1. And now we do the same thing. We choose a rational number between 0 and epsilon. Then R is between minus epsilon and epsilon, and it's an A because it's a rational number between 0 and 1. Right? So the intersection on E here, x equals 0. Right? So this is minus epsilon plus epsilon. So the intersection is not empty, and once again, x is 0 is an A bar. Right? The other case, third case, x equal 1 is completely similar to 1, but you just have to reverse. So you just have to take 1/2 1, and here 1 minus epsilon 1. Right? So just it's symmetric. Okay. So these three cases actually prove that 0 1 is contained in A bar, and therefore we have equality. So we really proved that A bar is the closed interval 0 1, and therefore A is not equal to A bar because A is strictly smaller than A bar. Okay? Since A is different from A bar, A is not closed and therefore not compact. Okay, so I suggest that you draw a picture to view what we are talking about. Now, the second way to prove that A is not closed is to find explicitly a sequence in A converging to a point not in A. Okay, so a point not in A, a typical point not in A is, for example, 1 over radical 2. It's not so but we can approximate 1 over radical 2 by a sequence in A. And we can do it explicitly actually. Okay. So define xn by this formula. Xn equal 1 over n times the floor function of n over radical 2. Okay? Partie entière. Now, by definition, the floor function of a number is between this number minus 1 and the number. I actually can flip the other way. So the number is bigger or equal than its floor function, and the number is strictly less than its floor function plus 1. So, but it's the same thing, right? So just the same thing written in two different ways, right? And now if we divide by n, we get what? We get that xn is between 1 over radical 2 minus 1 over n and 1 over radical 2. And for n big enough, for example, bigger than 2, this is positive. So actually, and of course, n is an integer and the floor function is an integer. So xn is a rational number. And this inequality proves two things. Proves that xn actually is inside 0, 1, and xn converges to 1 over radical 2, because when we let n tend to infinity, we get xn equal 1 over radical 2. So we have a sequence in A converging to 1 over radical 2, and 1 over radical 2 is not in A. So A is not closed and therefore not compact. Okay, so this concludes today's video. Next time, I will finish the exercise of chapter 1, but I will also have something to add as an appendix to chapter 1. There are two topics that I would like to talk about that I didn't mention in the lectures. Okay, so we will finish chapter 1 next week. Thank you for your attention.